Hello! Today we are going to talk about how to translate between different categories. So this is called having an adjunction. So the setup is as follows. I have some category over here. Let's call it C. And I have some category over here. Let's call it D. And I have some way of turning C's into D's. So I have a functor F here. So that means that if I have an object over here, which I draw a little dot, then I can map that to an object over here, which I also draw as a dot. So here I say the object is called X, and here the object is called f of X. Right? And if I have a morphism over here, which I draw as an arrow between the objects, then if this is called F, then I also get a morphism F applied to F here between f of X and f of Y. So I'm reusing the action on objects over here and the action on morphisms. I'm writing F for both of them and letting the context decide where it's coming from. Right. Okay, so let's assume I have this functor. So if you want to keep something concrete in mind, then this C here could be the category of sets, and this D could be some more complicated categories, such as the category of monoids, or the category of effectful programs, or category of topological spaces, or whatever you want. And now I have found some way of turning easy things into hard things, right, with this functor F. And now I would like to understand, how do I write programs that manipulate this f of X? So concretely, I would like to say, what does it mean to write a function out of f of X? So that means that we should have an arrow from f of X to some other object B, right? And if this B is of the form f of Y for some Y, then I could use the functor to do this, right? But in general, I'm interested in functions or morphisms into an arbitrary B. So now there could be some different situations. So there's my X, right? If I'm really lucky, then I can find a functor which goes in the opposite direction. So from D to C, such that it's the inverse of F, right? Because if that's the case, then I can just map everything here across to here and reason in my easy category where I know what things are like. But in general, I don't have such an inverse, right? Often my F is doing something which is not invertible. But I could still be in a quite good situation where I can't map all of this across, but I can see that functions out of f of X is the same thing as functions into g of B, where this B is the same as this one, right? So I'm not mapping the whole thing across, I'm just mapping the codomain across, and I get this funny little formula where I'm saying that a function from f of X into B is the same thing as a function from from X into G of B, right? So note that this here is happening in this category D, and this here is happening in C. So we are moving between the different categories. So this is called having an adjunction. I'm saying that F is left adjoint to G, or that G is the right adjoint to F, right? So F here is the left adjoint because it occurs on the left, and G is the right adjoint because it occurs on the right in the formula. And another notation for this is to write F and then a funny little backwards turnstile, and then G. It's F on the left here again, right? Okay, so there's one technical thing we still have to do, which is that this should work for every X and for every B, right? So what happens if we change the X and the B? Then we should still have a natural change in everything else, right? So let's say that I start here with morphism from f of x to b. So I'm going to use the hom to write these things now. So these are the homs in D from f of x to b. And then I have this way of going back and forth here to the hom in C of x and g of b, right? But now let's assume that I can do the same thing for some x prime and some b prime. So here I have f of x prime, and here I have b prime, and I should be able to go back and forth to the hom in C of x prime and g of b prime, right? So now, if you remember what it means to be a natural transformation, then this is starting to look like such a thing, if only we could put in arrows here, right? And we can, if I have an f from x prime to x and a g from b to b prime, then I'm claiming that I can fill in something sensible here. And what do I do? Well, if I'm starting with an h up here, then I want to make something down here. Okay, what can I do? Well, if I'm starting from f of x prime, then I can use my f here, and the fact that f, big F, is a functor, to go to f of x, and then I'm here in f of x, so I can use my h to go to b. Okay, and then I'm in b, and then I can use my g to go to b prime. Right. So that gives me a morphism from f of x prime to b prime. And what am I doing? I'm doing f of f composed with h. So I'm just going to write blank for that, and then g, right? And similarly here on this side, I can do the same thing, but now the first thing I do is f, then I use the thing I have from up here, and then I do g applied to the g. So now we have a diagram in set, right? So all the nodes in this diagram are sets. This is the set of morphisms, etc. And the arrows here are the functions between sets. So this was the to, and this was the from. The to, this was the from. So I can ask for this diagram to commute, and that means that these to and from bijections are suitably natural. And you could also make this precise by actually making this hom into a functor. And then this is just an ordinary natural transformation between two things. Okay, so this is how you would do all of this in Agda. Just encoding the information that we had before. So we have two functors, so that goes back and forth between C and D and C. And we're asking for the to and from morphisms that go between these things, right? Different directions. And we are saying that they should be inverse to each other. So if I start over here, I use to go here, and I use from to go back, then I should get back to the thing I started with. Right? And similarly, if I start here, use from and then to, then I should go back to the place where I started. And that's what it means to be a bijection. And then finally, we also need this naturality condition, right, which looks a bit daunting at first, but it's saying exactly what we said here, that if we compose in set first doing 2, so that's going here, and then doing this composition going down, that should be the same thing as first doing this composition going down, and then doing 2 for x prime and b prime, right? And it's in fact enough to ask that one direction is natural. Then you can prove that the other direction is natural using the fact that they are bijections. So you can look at this in your own time if you want.